Hey everyone. So Computerphile recently created a video that introduced monads to kind of beginner programmers and lay people. A lot of people seem to have a confusion or kind of issue with it because it introduced a bunch of extra ideas that didn't have anything to do with monads, and it also went on for a really long time. Um, and it kind of got me thinking, because as someone who studies category theory in school, uh, there aren't really a lot of good monad tutorials online. A lot of them kind of miss the intuition in a way that I think makes it frustrating for people trying to come to functional programming or just use functional ideas in object-oriented or imperative work. So what I'd like to try to do for you is give you a very quick tutorial about what the idea of a monad is and why you might care. So in one sentence, a monad is just that structure which you need to overload function composition so that some extra computation gets done on the middle value. That's really the whole idea. That's why they're used. Insofar as programming is concerned, that's why they're used. So the example that you would want to consider is you have a function f, which takes an integer and returns an integer. You have a function g, which takes an integer and returns an integer. And I want to compose them. I want to take my input, plug it through f, take that output, plug it through g, and then return that output. So this is a pattern that's going to come up a lot in programming because you want your code to be modular. But the thing is, you might want to do extra stuff after you've written these functions. For example, you might want to log each function call for debugging purposes. You would write the inputs to a string, or you might print them to the console, or do something like that. Or you might want to pass around a token, threading a token through each of these values, and then having your inputs and your variables kind of depend on the value of the token. This would be some way of simulating state in a persistent setting. And then, of course, if these functions can throw exceptions, you might want to escape from calling the rest of the functions and just return the exception that gets thrown. All of these things can be done by just overloading function composition. So the way that this gets implemented in practice is that you end up changing the type of your output like this. So fancy is kind of the M that's used in monad. So if you look in a language like Haskell, when you see M of int, this is this fancy. And all this is meant to indicate is that it's returning an integer that's been embellished in some way. And that's basically the idea. So I might write something like log of int, or this would be called state of int, things like that. And we create a new symbol for our overloaded function composition that looks like this. And again, this just means g composed with f in an overloaded way. From this example, you can also see that you could write list here, meaning that if I took in an integer input and returned a list of outputs, there's a possibility that I might want to, for every output integer in the list, plug it into G, and then concatenate the result. This also turns out to be a monad. So pictorially, what's going on is we're just overloading function composition. We're taking old composition, which used to look like this, taking a function from A to B and a function from B to C, and composing them to get a function from A to C. We're replacing that with this new thing called Kleisli composition, which takes an A to an embellished B, and a B to an embellished C, and returns an A to an embellished C. So I admit that up till this point, you're not really getting anything new from an imperative point of view. Sure, you're going to have to write some extra boilerplate, maybe write duplicate code in a bunch of places, but there's not really anything conceptually extra that this buys you until you realize the following thing. This overloading symbol does not change when you use a different monad. It's the same overloading symbol every time. And what the program is actually going to do when it sees this is it's going to look at the specific types that are being used. It's going to figure out which monad you mean, and it's going to overload that. So unless you specifically need to talk about a certain choice of monad, you can write your code for every monad. And that means you're getting polymorphism in your choice of monad. So I know that's kind of a complicated idea that maybe you're not used to. But the idea here is that you don't need to pick which one of these things you want to do when you write this code. You can choose just when you pass in the value which thing happens. So a common example that is used is a function called foldm. And we'll finish this explanation here. The payoff is basically that you can write code like this. Foldm, from an imperative point of view, does something like this. It assumes you have a binary operation, something like addition or multiplication, and you have a seed value. Oops. And based on that seed value, you also have a list of kind of values that you want to accumulate with. So for the addition example, I might choose 0 as my seed, and then this would loop through the list, summing all the elements up. Or for multiplication, I might pick the seed to be 1, and it would loop through the list, multiplying all the elements together. But again, because I'm thinking in terms of monads, my output might be embellished in some way with this m. So if we were to actually write this code recursively, what we'd get is something like this. So if I called foldm on a binary operation with a seed value with 3 values to accumulate, I would apply the binary operation to the first value, take the result, combine it with the second value, take the result, combine it with the third value. And this is function composition. And I'm not specifying which kind of function composition I want, so it means I can use any kind of function composition. So this code, depending on the monad that's used, could log each function call, as we said before. It could pass around a token. It could handle exceptions. Maybe this is division, and I want to escape if I divide by 0. All of these things would be handled by this same function, foldm. And so that's the power that monads buy you. It allows you to be polymorphic over an embellished form of composition.